In the last video, we left off at the cubic function. The cube right here is power 3, and now we're moving on to roots. So the first one we're going to do is the square root function. Please don't write anything down. I just want to illustrate a couple of items for you. In the past, we've been using these x values right here, and then we're plugging them or substituting them into the function. And then you get your values and you're happy and things mostly work out. Now, if I was to do that in this example, so don't write this out, just watch it. This is what's going to happen. So the square root of -2, if you put it inside a calculator, you're going to get an error. And the reason why you're going to get an error is because this number here is an imaginary number, which is I square root of 2. And that is in the complex number system, and we need to be in the real number system, which are irrational and rational values. So -2 would not be a value that exists for the square root function. Likewise, -1 would not be a value for the parent graph specifically. And that is because the inside of this function has to be greater than or equal to 0. So it has to be greater than or equal to 0. So that means in the parent function, I'm being very careful to say parent function, the negative values are undefined. And we'll see that. So try it in your calculator and you'll see what I mean. So now you can go ahead and start writing, because these are the things that you're going to need for this particular function. So we know that 0 is going to be defined. I just showed it to you. So I'm going to put 0 here and substitute it into the function, and I get 0. So that's good. That works out. 1. For x, if I take the square root of 1, that's fine too, because the square root of 1 is 1. Now, if I take the square root of 2, I do not have a perfect square root. In other words, if I punch it in my calculator, which is what I'm doing right now, what I will end up getting is an irrational decimal that goes forever and ever and ever and ever. But that's not what I want for my parent graph. So remember, these values are being picked in a very specific way. Likewise, if I plug in the square root of 3, I'll get another large decimal. But when you check the square root of 4, that goes to a perfect square root where it's a nice pretty number, and that's 2. So it makes sense that we would use 4 to get a nice value right on the grid. So the square root of 4 is 2. And just for fun, I'm going to do one more. So square root of 5, not good. These are not pretty values. Remember, they do exist, but they're just not pretty values. So 9 looks like it's the next value that would give you a nice pretty number. All right, so now we have our values for the graph. So I'm going to come over and start plotting the points. And when I connect the points, I get this nice smooth graph starting at 0, 0, and that's because, again, 0, 0 is defined. It looks kind of like, I like to think it kind of looks like a rocket being launched, but don't call it a rocket, because really the name of this is the square root function. And now we're going to do all of our analysis on here, or the characteristics. So domain. The domain are all the x values. And if you notice, there's nothing over here that are the x values. Those x values start right here, and that's at 0. And then we're going to include it, and it goes all the way because of the arrow to infinity. So the domain is 0 included to positive infinity. I'll have to rewrite that one. So 0 to positive infinity. Okay, then we are going to do the same idea with the y-axis. So we're doing domain now. So domain, domain, no, 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 there's nothing here. And when I get up to the top of the graph here, at y equals 0, the point is included, and we're going, here's the arrow, we're going to infinity. So this one is going to be the same. Remember, when we're talking about range, we're talking about the y values specifically. So even though they look the same, remember, they are not the same. Okay, now we're going to talk about increasing intervals. So increasing intervals, we're looking at going from left to right. And so this function, which is the square root function, increases from 0 to infinity. Remember, we do not include the 0 because it is not increasing or decreasing. So you do not include 0. It's everything up near 0, but not include 0. Okay, so the function is increasing from 0 not included to infinity. So there is no decreasing interval in this example. Let's look at absolute minimum. So the minimum is the point 0, 0, or is found at 0, 0. But remember, a minimum value is the y value. So the smallest y value is 0. There is no maximum because of the arrow. And then we're going to look at even and odd, which is the symmetry. So symmetry, if just in the most basic idea, is folding across axes. And if you look here, if you fold across the y-axis, there won't be any symmetry across the y-axis. And there won't be any symmetry with the two folds going this way and this way. So this has none. There is no symmetry. And then we don't have to worry about other. So that is the square root function. All right, next one. It's the cube root function. So just like on the last example, we needed to find perfect squares. This time we need perfect cubes. So what am I talking about? I'm talking about numbers that are 3 numbers multiplied together. And these are considered perfect cube numbers. So 3 times 3 times 3 is 27. And then likewise, so you should get pretty comfortable with doing these types of numbers pretty fast. So here's the thing. In the square root function, remember there's a little invisible 2. I talked about how the inside value here for the x could not be negative. Otherwise, you would get complex. Okay, this example works differently. So you have to keep the 2 types of problems straight. So I am going to fill in values here. And I'm going to start at 0 because that's a pretty easy one. Because we know that 0 times 0 times 0 is 0. So the cube root of 0 is 0. So that's easy. Fantastic, no problems. The cube root of 1 is 1. So as you can see, I'm doing kind of the easier ones. And then if I did the cube root of 2, I'm going to get that decimal again. Cube root of 3, and so on. So the one I'm really looking for is I have 0, I have 1. I'm looking for 8 this time. That's going to be the next x value that's going to give you a nice pretty answer for the cube root. So we're going to do 8. What's the cube root of 8? It's 2. So we have our positives and those feel okay, but now we need to go back and examine the negatives. So I'm going to start with -1 because it's just an easier number to work with, especially when you're learning these values with the cube roots. So what is the cube root of -1? Well, this is not a square function. So we're going to take -1 and rewrite it. And I'm going to show you why it's okay to have negative values for these cube root functions. So like before I said, 1 times 1 times 1 is 1 cubed. Well, negative times 1 can be written as -1. So this is all legal. But if you look at the parentheses right here, you can also write it as -1 cubed. These are all the same ways to represent this -1. So what you really have is you have -1 times -1 times -1. So now you have 3 of these. And I'm going to erase this. I'm just, running out of space. So this can be rewritten as -1 cubed. So at this point, the cube root and the power of 3, which is the cube, undo each other because they're considered inverse functions, which means I am left with -1. This shows that in the range, I do have a value that is negative. Okay, so I'm going to go through and I'm going to rewrite that pretty for you so that it makes more sense in the table. So -1, and then what I have is I have -1 cubed, which is equal to -1. So now I'm going to check, -2, no, you get a decimal that's, goes on forever and ever, cube root of 3, so on. The next one that is very nice, it works very nicely, is -8. You can see the symmetry here. So what is the cube root of -8? Well, 8 is the same thing as 2 times 2 times 2. So this can be written as the cube root of -2 with the power of 3. So I'm just putting my negatives back on so you can see what I'm doing. So that means when I simplify the cube root of -8, I get -2. Okay, make sure you're pausing that video and you're understanding where the values are coming from. Okay, let's go ahead and start graphing this now. All right, here we go. So -8, -2, all right, so what we really have here is this function that is being stretched across the x-axis. I kind of think it looks a little bit like a snake. Now, don't tell me this is the snake function because that's not the name of it. What is the name of this function? It's the cube root function. But if that helps you remember what the shape looks like, that's fine. But you want to always make sure you use the mathematics. Okay, now we're going to go through and do all the analysis. So here's the x-intercept. Y-intercept happens to be the same. Of course, this doesn't always happen. It's just in these parent functions. Okay, so then the domain includes all the x's. And if you look at these here, it's going to go all the way across. All the way across because of these arrows. So that is the domain. Okay, and then the range is a little trickier. You just have to make sure that you are keeping track of what you're doing. So let me do that in a different color for you. All right, I always start with my lowest value for y's down here for the range. Well, as you can see, I don't have anything written down here, and so it'd be easy to say no. But what you need to remember is this arrow goes on forever and ever and ever and ever and ever. And so eventually, yeah, you are going to have a value over here that intersects. It's just that we stopped the graph at -10. So be careful. So this really is negative infinity because of the arrows and the way. So for the y values, -infinity. So this one starts at -infinity and goes all the way up to positive infinity because of that arrow again. Okay, increasing. So this function is increasing on its domain. So you can see it because of the arrows. Again, we're going in left to right, and so it's -infinity to infinity. So parent graphs are very special. They work out real neat, but we'll be looking at other graphs that this is not the case. You just need to know how to identify things. All right, so we've shown that it's increasing over the entire function. So that means there's nowhere it's decreasing. Because of the arrows in infinite in both directions, there is no minimum and there is no maximum. Then we need to look at symmetry, and this does have symmetry. So if I take this part of the graph and I flip this part of the graph over the y-axis, I'll get something that looks like this. And then finally, I'll flip it over the x-axis and I will get that nice symmetry here. So this graph is odd. And I don't need to worry about other. So that is the cubic function. This is the radical or reciprocal function. You may have not seen this in detail as much in your other classes, and so it's a good idea to watch what's going on and then go back and write the notes. All right, so we're looking at rational or reciprocal function. So if you have the function f of x is equal to x, if I take this expression and I take the reciprocal of it, that's where this function is coming from. That's how the linear function or the identity function is related to the rational function. So I just want to make sure you make those connections. So these are the x values that are going to be considered our key points or our parent points that you will need in order to do this graph. So here we go. So we're going to evaluate the function. And I'm just going to make my pen just a little bit smaller, just a little bit big here. Okay, so I have -2, right? So the x values. And so this is -0.5. So I'll let you write those down. You're evaluating the function for each of the x's. Now, as you can see, I have left, and I think I'll do it with this highlighter. I have left the 0 without any kind of value. And that is because you might remember that we keep telling you as math teachers, you cannot have 0 in the bottom or the denominator. It's called undefined. But I'm not sure if you really know what that means other than just memorizing you can't have 0 in the bottom. So remember with fractions that 5 would be your total part. So if you had like 5 cookies, right? So you could take these 5 cookies and you could share them with somebody. So in this case, this is sharing it with one person because this is the part. So I'm just reminding you how fractions work. Now, if you have 0 in the denominator, what you're really saying is you have a total of 0 cookies. So if you have 0 cookies, you can't share it with one person because you don't have anything. That doesn't make any sense. And so it's what we call undefined because there's nothing to share. There's no total part that we're talking about. And that does affect our graph, which I'm going to show you. So again, that x value for this particular part of the function is undefined. All right, so we're going to start graphing those points again. You can see I zoomed in the graph for this one because the numbers are so small. So these are the 4 points that you're graphing. And I have left, let's see, and I have left this part right here not graphed yet, right? It's not graphed. So what you have is if this y value right here, so it's the y value is undefined, right? X is defined at 0, so that's fine, but it's the y value that's undefined. What we do is we create an asymptote, meaning, hey, this value does not exist for any value right here that's undefined. So this is called an asymptote. And you're going to be working with those quite a bit this year. So that may be new to you, but it's very doable. So the undefined y value is where that is coming from. So this is the equation going through the x-axis. So the asymptote is at x equals 0. So it's cutting through that x-axis here. You also have another asymptote, and we're going to be looking at this in more detail as we go through the rational section. And this one is at y equals 0. So this is the asymptote at y equals 0. So in your other, you may as well just write asymptote. Okay, so you have one at x equals 0 and you have one at y equals 0. So how does the graph behave? So it would be easy to think that you're just going to make a little rectangle here, a parallelogram, and that's what's not happening, okay? So I'm gonna actually go a little bit further. So this is my -1, or my +1, this is my +2. And now just for kicks, I'm going to calculate f of 3. So f of 3 looks like this, which if you turn it into a decimal, that's what you're gonna get. And if you look at this, 0.5 is bigger than 0.3 repeating, which means this number is smaller. You don't need to write this point. I just want to explain to you what's going on. And then likewise, if I put in 4, it would be 1/4, which is 0.25. That's even smaller. So that's what's happening with the asymptotes, is as we move towards infinity, towards the x's, so infinity towards the x's, my values here are going to get smaller for the y's. And so these asymptotes really tell us what the behavior of the function is going to be. And so the asymptote becomes very key in your graphs. And in this graph, we're not going to cross the asymptotes. Do not cross them. Some you do, but not in this section. Okay, take a look at that. Again, you're going to want to stop the video and go back and watch this one again. All right, I'm going to get rid of some of the stuff, and then we're going to look at the analysis. So we're looking at x and y intercepts. Well, if you notice, there are asymptotes where that value is at 0, 0. So there are no values crossing either axes, which means there is no x-intercept and there is no y-intercept. Why? Because of the asymptotes. Okay, so let's talk about domain now. So the domain, I'm going to get rid of some of this stuff for you. The domain are all the x values, and this can be tricky for some of you. So I want to make sure that we are all on the same page. So remember those asymptotes, and I say that because that's how you spell it. Those asymptotes or asymptotes are there even though they're not written in. So we have two parts of the graph this time. We have two parts of the graph. So the way I've been teaching you domain is eyeball it or actually write it in. And if you are to draw these values against the x-axis for the domain, remember these have arrows on this part of the graph. I don't want you to forget that, which means this goes on to infinity for negative infinity x's. But on the other side, eventually the part of the graph right here will hug that asymptote, but never cross it. So if it's never going to cross it, you're never crossing 0. Or you're never crossing the y-axis here. Okay, you're never going to cross it, which means we have negative infinity. So negative infinity. And we get up to 0 without actually ever crossing it because of the asymptote that we talked about. So we're not going to include 0. Don't include 0. We want to hook these two intervals together. So this is called union. And then we have to hook it with the part that's on the other side of the y-axis. So hopefully you can see there's that infinity, so it's going to be everything that's positive infinity. And then I'm not crossing that vertical asymptote again. So this is do not include 0 because that's where the asymptote is, up to infinity. Alrighty, so the next thing we're doing is the range. That's right. It is the range. So here's an arrow right here. So what that means that on the range, right, and I'm doing it with blue, is there a graph down here? The answer is yes. There is graph down here on the y's because I'm crossing the graph, that kind of purplish color. I'm able to cross it on the y's. And then we have that same thing happen where the y's are still crossing, but because of the asymptote, we're not going to cross it on this example. So I'm getting as close to 0 without including 0. So remember, this is negative infinity for the y values. So that's part of the range. I'm going to get as close to 0 as I possibly can. I'm going to hook the one part underneath the x-axis with the part that's above the x-axis. So you can see again, it works the same way. Here's your arrow. We're going to infinity. Yes, 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 as close to 0 without getting to 0. And so again, do not include 0 because of the asymptote, and you're going to infinity. Okay, let's look at increasing and decreasing now. Increasing and decreasing. And the way that I'm doing the graph is I know those parent points or those key values very well. That's why I can make the graph so fast, and that's what I'm going to be expecting you to do. It should almost be like second nature. If you really know these, you will not have to go back and look at your notes. And you will get this fast because we're going to be working with them all year long. Okay, interval. So if we're talking about intervals, remember we're talking about this direction. So you can see this part of the graph, and it's pretty clear, you can see it, is getting smaller for the y values. So we definitely know that this part of the graph on the x's for the interval are decreasing. So let's start with this one and see what's going on here. Okay, looks like it's decreasing too. So it's decreasing everywhere on the x's, remember that's the interval for increasing, decreasing, except at 0, because there is no value there, so it's neither increasing or decreasing. So I'm going to just go ahead and write those in. Now all of these match. They don't always match. Just on these parent graphs I mentioned. Oh, that is increasing. I put it in the wrong place, so I'm going to go ahead and fix that. So this doesn't work. There's nothing increasing, and then it's decreasing on the domain everywhere. Okay, absolute max and min. Well, we don't have a highest or lowest point because of all those arrows, and it's undefined at 0, 0. So there is neither a max or a min. Let's talk about symmetry. So if I take this part of the graph right here, and I flip it over the x-axis, and then I flip it one more time down. So this would be, if it was like this and there was a graph here, it would be even. But now I'm going to flip it down over the x-axis, and I do get the same image, so that is odd. So what are those characteristics that are the other? Remember, those are the asymptotes, just to remind you, make sure you have them. If you do not have the asymptotes on the graph, you do not have the parent function. Make sure you have the asymptotes on your graph. That's part of the actual exercise that you're doing. And we are finally at the end of this video for exponential functions. So as you can see, I did not put a grid on this example, and that is because I'm going to do the problem in generalities. So this is how this guy works. So the first thing I want you to take note is, this is the exponential function, and it kind of looks like this. Okay, so on a basic level, that's what it's going to look like. So what is the b, what is the a, and what is the x? You're not as familiar with this, but you will get there. Okay, so b is the base of the function. And it is a good idea to put a parentheses around that. X is the variable, and it is an exponent, which is where the words exponential comes from. And a is what we call the initial value. It's what you start with. Now there's some restrictions on this function that you have to be aware of, and I will talk about those later after we do the graph. All right, so you have to remember how functions work, exponential functions. So for instance, if I said evaluate the function at -2 for b to the -2, and I'm going to change that b into a number so it becomes a lot easier, what you have to remember is that negative in the exponent tells us to create the reciprocal to get rid of the negative sign. So it would actually be this. So I'm just reminding you how those negatives work. That's super important. So to make you understand this graph a little bit better, what I'm going to do is give you an example. F of x is equal to, let's say, 3 base 2 to the x. And all functions that are exponential work this way. What changes is the base. So there, you can almost think of it as there are so many different bases that could act as your parent function. So I'm going to use base 2 for this example to illustrate what's going on. So I'm going to start with the 0 because that's a lot easier to work with than the other ones. So I have, let's see, 0. So I'm going to plug in or substitute the 3 and the 2 and go to power 0. Okay. Rules of exponents says you do the exponent first. So I'm leaving the 3 there. What is 2 to the 0? It's 1. What is 3 times 1? It's 3. So that's the first value. It's 3. So f at 1, remember you do the exponents first. Just want to make sure that you understand that because it's super important. So in this one, we have 2 to the first power. So that's times 2. So the next one is 6. So the next value we're looking at is 2. So f at 2 is equal to a power 2. Remember, you do the exponents first. So this is the same thing as saying 2 times 2, and then of course you're multiplying by 3. So it's 3 times 4, which is 12. Change my color here. So what we have now is f at negative 2. So f at negative 2. And what we get is negative 2 okay, that's not what we get. So I've cleaned up my graph and now I'm going to start with the negatives. So remember, x is the exponent in this problem. So f at negative 2 is 3 times base 2 to the negative 2. So I'm going to come on over here and do a little work. So what you need to remember, and I showed you previously, is that negative sign tells us to take the reciprocal of the whole expression. So that is what I'm going to do. So I'm flipping the 1 to the top in the numerator, and I'm moving what's on the top down below, and the exponent becomes positive. So this is 1/4. So that is actually what the number is for the exponent on this one. So I'm gonna color code it so you understand where it's coming from. So this ends up being 3 times 1/4. So that's 3/4, which I'll put the decimal there. It's 0.75. So it is a small value. So keep that in mind. Okay, so I'll clean that up for you. So f of negative 2 was 0.75. Okay, so now we're doing f of negative 1. That's why I like to start with my positives first and then work backwards. Do the no-brainers first, right? The ones that are easy. Okay, so this is 3 times base 2 to the negative 1. I'm going to come do some scratch work out here. I'm going to take the reciprocal to make the exponent positive, so I get 1/2 this time. So 1/2 is going to be multiplied by 3. which if you do that, you get 3/2, but it's 1.5, which is fine with me. If you noticed, I did use decimals for some of these, so go ahead and write those out. So I'm just going to clean this up so then we can start the graph. Okay, here we go. We're going to start graphing. And I know I didn't leave any values for the y, but that's because the exponential graph grows super fast and I want to make sure that I had plenty of space and not confined by the axes. Okay, so I'm going to start with the easy ones like I said. So 0, 3. So maybe I'll go 5 here. So 0, 3 would be right there. And then 1, 6. And then here it is growing really fast. Here's 2. And then let's see, that's 10, that's 15. So 2 is 12, is like right there. So I'll go back and do it in black so you can see the points a little better. Okay, so those are the positive values. So that's these guys right here. Now I'm going to do the negative values. So what are the negative values? Here's the x's. And when I graph them, you can see that they're pretty small numbers here. So at -1, I get 1.5. So if this is 5, it's going to be pretty close to the x-axis. And then at -2, it's even smaller. So it's half as small. So now we're getting super close. And if I keep going, I'm going to get super small numbers. And so what happens is we have another case where we have an asymptote there. So now I'm going to complete my graph, and I'm going to put that asymptote there based on the fact the y values are getting super small. So we're not going to cross this asymptote. So let's do the have no x-intercept because the graph never crosses the x-axis. Now we do have a y-intercept, and that y-intercept was at 0, 3. So now we're going to look at domain. So you can see hopefully that the graph is going to go to infinity for the x's here, and it's going to go to infinity over here. And if you don't recall why that is, I'm going to draw those lines. Remember, it's going to infinity, so it's going to be everything on this side. Okay, which means the domain, it runs from -infinity to infinity. Okay, what is the range? Well, I have no graph here. No. Okay, I start having some values for y starting right here, but I do not include 0 because of the asymptote, right? It's that bounce. Like you get super close to 0 without ever touching 0. So if I go on the other side of the axes, I now have values up to infinity. Okay, so I hope the domain and range are getting easier for you. Okay, these are those parent values again. All right, where is the function for this increasing? Well, I'm going in this direction. So if I was to draw those little arrows, I'm now increasing everywhere on the domain. So it's -infinity to infinity. I'm not decreasing anywhere because I'm increasing everywhere. Okay, I do not have an absolute or a definite smallest value because of the asymptote, because I'm still going to get values that are positive here. Never going to get anything smaller, okay, or negative. And then there's no maximum because of the arrow on the other side here. And then we need to talk about symmetry. If I fold the function across x equals 0, which is the y-axis, I'm not going to get that nice symmetry. So it is not even. And if I fold across the y-axis and I fold across the x-axis, I will not get symmetry. So this is neither. So it's neither, even, nor odd. Now you do have an asymptote, and the asymptote is at y equals 0. Because remember, it's horizontal, it's cutting through the y-axis.